Okay, it should work, great. So basically, I will show you how the interaction between these systems and human beings can be enhanced by named entity disambiguation, and I will provide details on that. I will also show you how knowledge graph can be used to further improve this type of interaction. And finally, I will conclude describing the advantages of in adopting knowledge graph compared to pure language-based models. So let's start with the context related to the intelligent advisory systems that can be really useful to support different type of healthcare, different types of stakeholders in the healthcare domain. These stakeholders include, for instance, clinicians, researchers, insurance companies, and obviously patients. And all these stakeholders have specific goals, but at the same time have distinct responsibilities. The subset of the requirements to construct this type of intelligent systems include the capacity of detecting meaningful entities within natural language communication. And on the other side, these systems require the background knowledge to ground the interaction between the system and the human being. In order to be more specific, in the case of question answering system, for example, we need to detect entities both in questions and answer. And at the same time, a background context is really useful in order to drive the conversational flow. How we can meet both these requirements? Well, in regards to the meaningful entities, we need a reference knowledge that is focused on the application domain that includes these meaningful entities. And at the same time, in order to inject this background context, we need to incorporate, and organize in a coherent way information coming from multiple data sources. Actually, the knowledge graph is a flexible solution to address both these requirements, because on the one side, the knowledge graph can become the reference knowledge to depict the meaningful entities. And on the other side, the knowledge graph can set the background contextual information in order to drive, for instance, the conversational flow. In the knowledge graph, obviously, you have nodes that represent real-world entities. You have edges that define meaningful connections between these entities. And data coming from multiple data sources can be integrated in a flexible way into this graph structural representation. Actually, this is not enough, because in order to exploit the power of knowledge graphs, we need the technological ecosystems and platforms that are able to manipulate all the features of this knowledge graph. In GraphAware, we developed a platform that is called Hume, that is able to ingest structured and unstructured content using an advanced orchestration mechanism. And with GraphAware, you can visualize your knowledge graph, you can interact with it, and you can perform graph-based analysis in order to detect, for instance, specific patterns within the data. Actually, this is the only slide, Francois, on the product, I promise. But I have another one. So basically, we describe the role of knowledge graph to build intelligent systems. We describe the need of technological ecosystems, and considering our first requirement, so basically the reference knowledge focused on the application domain, the main question is how to link detected entities within the text to this reference knowledge. The named entity disambiguation is the task to perform this linking step from a mention within the text to entities located into reference knowledge. And in order to have a better intuition on named entity disambiguation, consider this a specific example in the healthcare domain. Glitazones may be used for treating this type of diabetes that is mainly related to the lifestyle. Here, the main goal is to link these highlighted terms to a reference knowledge. In order to consider as an example of reference knowledge the unified medical language system, that is one of the most prominent thesaurus that is able to collect entities and concepts coming from different data sources in the healthcare domain. The first phase in this case, for the linking step, is to recognize glitazones and diabetes as named entities. So glitazone, the first one, refers to a chemical substance, while the second one refers to a disease. This is not enough, actually, because as you can imagine, with the terms diabetes, we can consider distinct diseases like type 1 diabetes, type 2 diabetes, or still gestational diabetes. So basically, we need a mechanism mechanism in order for disambiguating among all these candidates. And this is the role of named entity disambiguation. And in the next slide, I will show you how some entities are represented in a unique way within the unified medical language system. This is an example of the page related to glitazons. As you can see, there are multiple structural information, such as, for instance, the description, the semantic type, a set of broader related concepts. Actually, the real name was glitazons, so they mentioned it in the text, which is one of the names that we can associate to this specific chemical substance. To have a better understanding of how traditional named entity disambiguation systems work, consider this simplified schema. In named entity disambiguation system, we can distinguish two main phases. The first phase is the candidate selection. So considering the specific mentioned diabetes, these terms can refer to different types of diseases, as we already said. And the second main step is the ranking step. So basically, we have to assign an order to these specific multiple candidates that can be associated with the mention. So in this example, type 2 diabetes achieves the best results because there are some keywords in the context like glitazons or lifestyle that in general refer to this type of disease. If in our sentence we would have other words like genetics or, for instance, pregnancy, these words would be signal for other types of diseases. As you can imagine, there are not trivial challenges when you have to perform named entity disambiguation. We already mentioned some of these challenges because with the same terms, we can identify different diseases in our case. But from another point of view, from another perspective, distinct terms in many cases can have a very close and very similar meaning. Consider, for instance, the case of type 2 diabetes. We can define these diseases using expressions such as non-insulin dependent diabetes or ketosis-resistant diabetes. The current approaches for named entity disambiguation leverage pure language models that exploit transformer-based architectures. And in general, in order to represent the mention and the candidates, we exploit the contextual information coming from models such as BERT. For the candidates in particular, usually we use the structural information such as the definition or the semantic type that I will show you before for the unified medical language system. Actually, these approaches have some limitations because in many cases, there is an incompleteness of these structural resources. So for instance, metadata that can be useful to distinguish a protein or a gene that have similar names, in many cases, this metadata is missing. At the same time, there is a low coverage of entities in terms of annotated data sets. So we do not have a lot of examples in order to train our model. And the solution in order to address this lack of information is to incubate further huge annotated data sets. And this creates, let me say, in many cases, scalability issues. So we have to understand how to address these limitations. And considering our second main requirement, so the injection on additional background knowledge in order to, for instance, drive the conversational flow in a question answering system, we should understand how we can enrich our data, so how we can integrate concretely this background knowledge. And this is the case, this is a situation in which the knowledge graph comes to play. Because in a knowledge graph-based perspective, we can transform knowledge bases such as the unified medical language system into a graph structure, into a knowledge graph structure. And then we can exploit the meaningful connection within this knowledge graph structure to learn a new representation for the candidates that is not based on the structural information that are often missing, as we had said before, but directly on the graph structure. We can inject further information, let me say, incorporating ontologies that are related to the application domain. So when we perform this enriching step, our target entity from the named entity disambiguation becomes just an entry point to enable discovery and explainability. And you can create with this tailored information new connections that are not so trivial. So for instance, consider a document that mentions a specific disease. And this document can be connected to another document that mentions, for instance, a symptom or a phenotype that is connected to this specific disease. So no trivial connections. And exploiting knowledge graphs and exploiting technological platforms to manipulate this knowledge graph, we can interact with it, we can detect patterns, and all these features enable the opportunities to explainability and to the refinement of the model, like a named entity disambiguation. From another point of view, we can state that the knowledge graph enables a virtuous circle around the named entity disambiguation system. Because on the one side, as we have seen, the knowledge graphs can empower named entity disambiguation system for the entity linking step. But on the other side, named entity disambiguation system can be employed in order to create new version of a knowledge graph and extended versions of a knowledge graph. I'm going to explain this virtuous cycle starting from the first side. So basically, this is our well-known schema on named entity disambiguation. As we already said, we can transform a reference knowledge into a graph representation and then exploit machine learning techniques applied on graphs in order to encode a new representation for the candidates. And this new representation can be used in our specific case for the ranking step. I remind you that the ranking step has the goal to assign a score to the plausible candidates in order to detect the target one, considering our annotated sentence. I'm going to explain a bit of technical details, this part. So I remind you that the input of the ranking step includes the annotated sentence. It includes the multiple candidates that can be associated with the mention. At the first step, we can, for the annotated sentence, we can learn the word embeddings of the sentence, and we take into consideration also the sequential information. So we want to encode also the sequential information of these words. This is the meaning of LSTM, so that stands for long short-term memory. And for the candidates, we can perform, apply graph knowledge embedding techniques in order to learn the no representation of the candidates within the graph. Then we can combine this representation from these two different vector spaces through a concatenation process. And we can use this combined information in order to train a neural network as a binary classification model. So in this neural network, we consider as positive or true example the target entity, so in our case, type 2 diabetes, while the negative and false examples are the other candidates. So in our case, type 1 diabetes or gestational diabetes. So as output of the model, we will achieve a score between 0 to 1 for each of these candidates, and we can use this score to perform the ranking step. Now let's see the other side of this virtuous circle in which named entity disambiguation system can be used to build and enrich knowledge graphs. This is our schema, and we can put the output, we can publish the output of a named entity disambiguation system within a knowledge graph. Then we can enrich this information incorporating domain ontologies. And this enrichment process creates the condition for the background knowledge that we need to create intelligent advisory systems. In these details, in this background knowledge, we have information such as glitazone's treats type 2 diabetes, or type 2 diabetes is a long-term chronic condition. It is usually onset on adulthood, and it can be kept under control with an healthy life. So we have all the ingredients, right? It seems a complex process, but actually in Hume, we have a specific feature called orchestra that provides an intuitive interface to decompose a complex workflow into a linear structure. So basically, each of these components takes as input, I don't know, structured or unstructured information, information coming from REST services, etc. Each component processes this information and provide an enriched version of the initial data, of the input data. I'm going to conclude this presentation stressing the advantages in adopting knowledge graphs for named entity disambiguation and for building intelligent advisory systems. Because in the case of knowledge graph, we can exploit the graph structural information for the representation of the candidates, so for encode this type of representation. Considering technological platforms, ecosystems, and the knowledge graph itself, we can include the human in the loop in order to improve the knowledge graph, and as a main consequence, improve the performance of the named entity disambiguation system. Obviously, the knowledge graph, as you already heard during this conference, enable a lot of opportunities in terms of transparency and explainability compared to traditional and pure language-based models. Actually, your journey can start here for building intelligent systems using knowledge graphs, because we said and we specified that the knowledge graph provides all the ingredients to build intelligent systems. Not all, but some of the requirements that can be really useful. We have seen how knowledge graphs enable the construction of a virtuous circle around named entity disambiguation systems. And obviously, the user can interact with this constructed knowledge in order for discovering and for better explanations on the results. I would like just to mention the books about these topics. In particular, one book is already available called Graph-Powered Machine Learning, written by our chief scientist, Alessandro Negro. And actually, we are working on another book called Knowledge Graph Applied, whose MIP will be released, hopefully, in this month. So I would like to thank for your attention. I'm available here for the questions, and also upstairs to the booth with you will find me, Alessandro, and 3 copies of the book. So thank you very much.
Thank you, Giuseppe. So we have time for questions. Yes.
So nice presentation and good talk.
Thank you.
You showed a slide where you had the language model on one side,
yeah,
and the embedding from the knowledge graph on the other side to do the disambiguation, right?
Exactly, yeah.
My basic question is, we are doing the disambiguation for the knowledge graph, right? Now, when that becomes an input, how does that work? So are you trying to say that's an iterative process that you're trying to show there? Because we're going to build a knowledge graph with entities disambiguated. So how can we use that as an embedding is my question.
Yeah, actually, I think that what you said represented the first side of the virtuous cycle that I described in this presentation, because one possibility is that you have your annotated sentence and you have a reference knowledge graph from which you want to link, right? So basically, you want to understand which of all the entities included in the knowledge graph effectively describe the meaning of the mention within the annotated sentence. So basically, this is the way in which you can exploit the knowledge graph embeddings, because when you perform the candidate selection, you identify the multiple candidates from this knowledge graph. But with these multiple candidates, you have also linked the related embedding representation. So basically, when you detect the multiple candidates, you can use the related embeddings in order to train these neural networks, to train this classification model. So basically, you perform the learning step of the knowledge graph embeddings offline. So basically, you perform, then you learn the knowledge graph embeddings, and then after the candidate selection, you will get the embeddings of the multiple candidates, and then you concatenate these embeddings with the representation of the annotated sentence, and then you train your model. That's the main idea.
Thank you, Giuseppe. Farka, can you show the Q&A, please?
I just had a quick question about like how you're actually generating the candidates in the first place. Is it just like string matching, vocabulary lookup?
Yeah, actually, in our approach, we would like to maintain the explainability and the interpretability of the results as much as possible. So basically, we use right now Elasticsearch. So basically, we store all the information related to the Unified Medical Language System that provides, for instance, all the names that are related to a specific disease, and we fine-tune some queries in order to get the candidates. We are also experimenting in using language models to make, let me say, a sort of a pre-rank of the candidates in order to have just a well-defined number of candidates for performing the ranking step. So basically, we use the Elasticsearch for now for the candidate selection.
And are you only using knowledge graph to disambiguate if there's more than one candidate, or?
Yeah, exactly. For now, yeah.
Questions?
Thank you. That's a great talk.
Thanks.
So from what I understand, you used the graph structure to build the embeddings for the entities in the graph.
Exactly. Yeah.
How does that perform for like entities with low connections? Does it has a negative impact on that?
Well, actually, for now, we try to evaluate our approach using specific data sets that are available within the research, because in order to have just a comparison, and I think that we are close to the state of the art in terms of evaluation data sets that are available in this specific domain. I think that we need some tuning in terms of hyperparameters, or we would like to test more models in order to learn the embeddings, because for now we are just trying specific knowledge graph embedding techniques like dismult, but we would like to incorporate also graph neural networks in order to see if we are able to improve the performance. So basically, I think that we achieved the good results considering the evaluation data set. So basically, we are trying to also, we are involved in projects, for instance, with the Rockefeller Archive Center in order to test this type of approach for annotating the documents in their archive. So we will see how it works in real world.
Any other question? Online, still, Farka, is there something? All right, well then, Giuseppe, thank you.
Thank you very much, Francois.
We have a break now, I think.